Hi friends, in this video we'll be dealing how to calculate the magnetic field in some common situations which we encounter. The first one is current carrying circular loop. Say this is x-axis, y-axis and z-axis, and let current be in this direction and let the current be I, and radius of the circular loop is r and center is at origin. Okay, now I want to calculate the magnetic field due to this current carrying loop at this point P, which is at a distance x from the origin. It is on the x-axis. Now what I'll do, first I'll consider a small element here, dl element, and first I'll try to calculate the magnetic field due to this element only. You know that the magnetic field is given by this one, dB is equal to mu naught by 4 pi I dl cross r by r cube, right? Where r is the radius vector. Now the dl here is tangential to this circle. Of course it is everywhere tangential, and the radius vector is this one from here to here. Okay, that's a straight line, and this is the radius vector. By right hand rule, this cross this gives me the magnetic field in this direction. Okay, this will be my dB. Now observe carefully, this dB I can resolve this one into two components, one perpendicular and one parallel. Okay, parallel to the x-axis. dB perpendicular is here. Now let me take one more element here, dl, which is diametrically opposite to the first element. Here the dl vector is in this way and radius vector is this one, and again by right hand rule I'm going to get my dB in this direction. It will be of the same magnitude, but the direction is this one. What happens here is, even this vector I can resolve into two components, one is perpendicular and another is parallel. Are you observing it? This perpendicular vector and this perpendicular component gets cancelled because they are opposite to each other, and the parallel components gets added up. The similar thing happens with every element. The perpendicular components of that element with the perpendicular component of the diametrically opposite element gets cancelled, and finally you only have to add up the component which is parallel to the x-axis to get your final magnetic field. Okay, now I want to calculate the horizontal component, that is component which is parallel to x-axis. What will I do? This is dB, right? If this angle is theta, say, so my this component which is parallel to x-axis will be dB cos theta. Everything is fine till now. Now I'll integrate this one. First of all, let me write this. dBx is equal to dB, which is nothing but mu naught by 4 pi I dl cross r by r cube into cos theta. Okay, now let me deal only with the magnitude so that it becomes easy for me, because anyways I know the direction, right? So mu naught by 4 pi I dl by, here I have into r cap by r square. I can write it as into r cap by r square, right? Anyway, I know the direction, so I'll directly write this one as r square as x square plus r square, where capital R is the radius of the circular loop, and okay, I have costed also. This is my dBx. When I integrate this over the circular loop, I mean I add the all horizontal components of all the elements, then what I'll get, instead of dl, this dl gets summed up to the perimeter, right? Then finally I'll get I 2 pi r by x square plus r square. Well, what is cos theta now? If this is theta, this becomes 90 minus theta. So this is theta again. If this is theta, what is cos theta? R by root of x square plus r square. So I'll write r by root of x square plus cos square. That will be this one. Everything is clear till now? Of course, this is the final answer. This is the integral of dBx. You can write the same thing as mu naught I r square by 2 x square plus r square whole power 3 by 2. in the I cap direction. Here your direction is I cap, and normally if you want to get the direction, you can either use the right hand rule or take this one. If this is your current direction, and place your right hand such that the curl of your right hand fingers give you the sense of the current in the loop. Then your thumb points the magnetic field direction. Either follow this, or you can also take this. If you're facing the current loop, if you're facing the current loop and the current is moving in anti-clockwise direction, then magnetic field is towards you. And if you're facing the loop and the current is in clockwise direction, then the magnetic field is away from you. Hope everything is clear till now. There is a special case here. This is the formula, right? What happens if you put x is equal to 0? Then your B becomes mu naught I by 2r. This is the magnetic field at x is equal to 0. That is at the center. Okay? Direction you can anyway get it from the right hand rule. I hope everything is clear till now. In this situation, current is going like this. Okay? Now I want to calculate the magnetic field at this center. Observe this. There will be no magnetic field due to this part and this part. Because the length dl vector of any element in this part of the wire will be parallel or anti-parallel to the radius vector, right? So you're not going to get any effect. Finally, I'm going to get the magnetic field only due to this semicircular part, which will be mu naught I by 4r. You know that mu naught I by 2r is the magnetic field when you have complete circle. Since it is a semicircle here, you have mu naught I by 4r, okay? And the direction is from the right hand rule. Here it is this one into the paper. And if you had a situation like this, then it would have been this one coming out of the paper. Okay, let's move forward. Next, I want to calculate the magnetic field due to infinite wire, straight wire, of course, current carrying conductor. Now, either you can calculate the magnetic field at this point by considering each dl length element and adding up the magnetic field due to each all of these elements, and finally you will get the answer. But no doubt it's going to be very cumbersome. And to simplify this, we have a law, or I should say it's a gift. It is something similar to Gauss law. In electrostatics, we had Gauss law, and here it is the Ampere's circuital law. What it says is that if you have a loop, closed loop, and you have some currents passing through it, what it says is that take any length element, the dl, you have a magnetic field right at the surface, at this perimeter, and the dot product of this magnetic field and the length vector dl, when you integrate this one over the entire loop, the final product you are going to get is mu naught times the current enclosed. This is the mathematical form of Ampere's circuital law. Hope everything is clear till now. This loop is normally called as Amperian loop, and note that this is the dot product. Okay. Now, I'll try to take the advantage of this law to find magnetic field due to a infinite wire. Okay. What I'll do, consider a wire carrying a current I. Of course, this is an infinite wire. I'll assume this circle as my Amperian loop, and my current carrying wire is passing through its center. Okay. By symmetry, I can say that the magnetic field at all these points on the circle will be same. Of course, the direction will be different. It will be tangential to this loop at all the points, but the magnitude will be same, right? Let it be B. And here the dl length vector is also tangential. So of course, not only here, everywhere it is tangential, and the magnetic field is also tangential. So the dot product is just the product, right? I can just integrate it and say that it is mu naught and mu naught times I. Okay. Now, what is this integral? When I integrate this dl element over the circle, I'll get the perimeter, right? So into 2 pi r be the radius, mu naught I. So what can I get from this? Magnetic field at a point which is at a distance r from the current carrying conductor, will be mu naught I by 2 pi r. See how simple it became for us to calculate when we took the advantage of this law. Hope everything is clear till now. What about this? If you have a circle, ampere and loop here, and you have current passing through this, not through center but something else, and you have the same current I passing through it, you can't say that magnetic field is this thing at all the points. No, that's wrong. Because in this case, we took the advantage of symmetry. Through symmetry, we said that the magnitude of B is going to be same at all the points. Here, it's not the same case, right? Even here, the Amperian law holds true. The final product of B dot dl when integrated will be equal to mu naught I, no doubt about it. But it doesn't mean that magnetic field is constant at all the points on the loop. Okay. Now let's solve a problem. This is a wire of thickness capital. No. This is a wire of radius capital R, say, and it's carrying a current I in this direction. Okay. Now I want to calculate the magnetic field at different points. Now, when I want to calculate the magnetic field at this point, which is outside the wire, it is at a distance small r, say, from the center of this or from the axis of this wire. Then my formula will be same. B is equal to mu naught I by 2 pi r. Now, when I want to calculate the magnetic field inside the wire, what I'll do, I'll assume a Amperian loop here. If I want to calculate the magnetic field at this point, let this distance be smaller now, but the current passing through this Ampere loop, it's not I now. So my new current will be I r square by r square, and current times mu naught gives me the magnetic field, right? No, it doesn't give me the magnetic field. It gives the magnetic field times perimeter. What is it? 2 pi r here. So what can I say from this? My final B here will be just a minute, mu I r by, my B will be mu naught I r square by r square by 2 pi r, right? This will be equal to mu naught I r by 2 pi r square. When you want to calculate the magnetic field at a point which is inside the current carrying conductor, I mean to say that when r is less than r. Observe this. Here it is linearly varying with the radius distance from the axis from this r, whereas here it was inversely proportional to the radius or the radius vector. So when you draw a graph between magnetic field and distance from the central axis, you'll get something like this. First, it will linearly vary with it till the distance becomes capital R, and then you have this where B is inversely proportional to R. Here B was directly proportional to R. Hope everything is clear till now. That's it for today.